Okay, so you asked about the formal definition of the limit. I apologize, it's taken a while. Thanksgiving kind of threw me off. I was off for a couple days and still trying to get caught up with everything. So, the formal definition of a limit. Let's talk about an informal definition of a limit first. So, a limit is saying if you have a function. So remember, a function has every domain value going to one specific range value. So you can't have any repeats. You know, if this graph kind of curved around and went back, you can't have any going from top to bottom that match. This x value goes to one up here and one down here. So it has to be a function. As you get close to a particular x value, so I'm going to actually pick one. I'm going to say 4. Let's say we're going to travel on the graph and get closer and closer to 4. Then your limit is the range value, the y value, that you're getting closer to. You know, if you're over here at 6, you're at like 6, 3. But as you get closer and closer to 4, let's say we're at 2. So as you approach this x value, what's the y value? That's your limit. Now, this can also apply if you have a graph with a hole in it. A graph with a hole is still a function. So if this is still 4, 2, you're still approaching 2. As you go closer and closer to 4 in the x direction, you're still approaching 2 in the y direction. Here, you could actually reach it. You have a defined y value. Here, there is no defined y value, but the limit would still be 2. So f of 4, your x value is 4, would be 2. Nope, sorry. That would be the limit, would be 2. F of 4 would not exist on this second graph. And the limit, as you approach 4 of this function, would equal 2. A limit would exist, but a y value doesn't exist. On this one, the limit and the y value are just the same number. Y value is 2, limit as x approaches 4 of the function also is 2. So that's our general concept of what a limit is. But for a mathematician, you need some proof. You need, well, this will work every single time, no matter what. So that's where this formal definition comes in. They needed something to give a better definition so we know this is what it is every single time. So let's look at this formal definition. Starts out with let f be a function. So a function, not a relation, no repeated range values. Defined on an open interval. So that's saying it could be this entire graph that's going forever, or maybe you just limit it to a smaller piece and only take this like small inner piece, as long as it contains c. So this value that we're trying to approach, that we're getting closer to in the x direction, is c. So our interval, we couldn't do an interval, pick a different color. I couldn't do an interval up here because it doesn't contain the c we're currently looking at. So then it says, except possibly at c itself. That's to cover this situation. We still want this to be around the value that could exist, but on this particular graph there's a hole, so c doesn't actually exist. But your interval can't have any other holes. You can't have another hole and still consider this a good open interval. And let L be a real number. So L is what stands for your limit. If this value is c, then 2 is your limit value. If for all epsilon greater than 0, there exists a delta greater than 0. So epsilon and delta are just usually used to represent small numbers. You know, you're not usually going to see an epsilon that's 100. Usually you'd see, a 0.01. If you have a really, really small interval, then you're going to get closer and closer to those y values. So delta is associated with your x values. You have x minus c. So x values. Epsilon is associated with your y values, f of x minus l. So what delta is saying is I could pick this interval. Let's say I pick this interval and I'm at 5 and I'm at 3. And that gives me a y value of 1 and 3. So my delta range is I'm not smaller than 3, but I'm not bigger than 5. So I'm going from 3 to 5. And then my epsilon range would be I'm going from 1 to 3. Well, that's a pretty big interval since we're trying to get super duper close. Limits are trying to get basically infinitely close. So we want to be able to pick a smaller interval. Let's say we pick 3.5 and 4.5, so 3.5 and 4.5. So now my delta is going from 3.5 to 4.5. My interval's a little bit smaller. Well, this whole sentence is trying to say if you make that interval smaller for your delta, it should force your interval smaller for your epsilon. So on this graph, let's say it's 1.5 and 2.5. We got a smaller epsilon interval as well. So that's our goal with these intervals, is we want to get them super small so that we're getting closer and closer in the x direction and closer in the y direction. Okay, so I'm going to go to a new page. There's a lot of writing going on. I'm going to draw that same approximate graph. This is not, super accurate. And let's leave the one with the hole in it. So we have 4, we have 2. So now when we picked our intervals, we picked this value above, this value below. But with the epsilon and delta, usually we're just going to define those first and use those to find our interval. So for delta, it said 0 less than x value minus c less than delta. So let's say we want our delta, and I'm going to stick with kind of larger numbers just because they're easier to draw and see, and then we'll move to the smaller numbers eventually. Let's say we just want delta to be 0.5. So this x minus c part is saying, so 0.5, that means I'm going to be 0.5 above 4. So to figure out that value, I would do 4 plus 0.5. So that actually gives me the value of 4.5. But they're going to write it way more general. So we said the one we're approaching is c. So 4 is c, x minus 4. And we defined delta, but let's say we hadn't defined delta. So let's say we're back here. That means this is c plus my delta. That's going to give me one part of my interval. So this is really c plus delta. Then if we wanted to find the other side, we'd have to do c minus delta. You'd do 4 minus 0.5. So if we wanted to find the other side, you're doing c minus the delta. For the one we picked, that would be 3.5. So that means the x values you can choose from, so x is always this variable because you can choose it. You could choose 4.2. So if you did that, if you chose 4.2 minus 4 less than 0.5, well, is this going to be a true statement? 4.2 minus 4 is 0.2. Absolute value of that is still 0.2. So yes, we get a value that's smaller than 0.5 but bigger than 0. So the absolute value bars are to take into account this left side because it's going to give you negative values. If you picked like 3.7, 3.7 minus 4 is negative 0.3. So we need to absolute value bar it so that it gives you a positive here so that you're still between 0 and this 0.5. So between the 0 and the delta. So your x that you're choosing, it can be somewhere between c and c plus d, so that interval, or it could be somewhere between c and c minus d, minus delta. It could be in that interval and still make this statement true. So the goal is to get a small enough interval that eventually you get so close that all the x's you're picking are basically 4. You know, if we got closer and closer and closer, we'd get 4.000000001, which with, you know, that small of a decimal is basically 4. You're trying to get it to be the same value as 4 pretty much, even though it never does actually equal 4 for the limit. It's never that x will equal c. You're just getting so infinitely close that you might as well be 4. The limit is just a really weird concept. So with those x values, that will limit your epsilon interval. So your epsilon interval is going to be related, you know, I didn't write out an actual function, but you could plug in, you know, if the function was x plus 1, you could plug in 4.5 and get the y value. So our epsilon interval, same idea, is epsilon is basically this distance away from the y value you're trying to approach. And it will be forced. If you pick delta, epsilon is going to be a certain amount. If you pick epsilon, delta is going to be a certain amount. So this is our limit value, and this is also our possible y value. Again, if you have a hole, the y value may not exist, which is why you can't just always say f of x is going to equal the limit. That's not always true. It's sometimes true, not always true, which is why we need these really weird epsilon and deltas. So just like here, this would c plus d. This here, one end of your interval will be L plus E plus epsilon, and one end will be L minus E. And it still fulfills that absolute value bar requirement so that you can take those values above and those values below and have it match. Have it still fit this inequality. So again, we want our y values to be limited to this interval, and as we pick smaller x values, we're hoping our y values become closer and closer to that limit number. So those should help you with the first two problems. Let's actually apply it and do a problem now. So let's say we have the limit as x approaches 1 of the function 3x plus 1 equal to the limit of 4. So this is, you didn't actually have to find the limit. This number here is L. It's the limit. Then it's going to ask you, find the largest value of delta such that epsilon is less than 0.005. So if we were to graph it just to show the picture in relation to those previous discussions, let's see, we start at 1, up 3/1, and we have a line. We're approaching the x value of 1. So we're trying to approach this x value. And if epsilon is limited to 0.005, technically you're trying to find between the y values of 4.005 and 3.995. And that's hard to draw since they would be so close to 4. So according to our formal definition of a limit, f of x, absolute value of f of x, minus the actual limit value is less than epsilon. So we have lots of this information. we know epsilon, 0.005. We know the limit, that's 4. We know the function, f of x is 3x plus 1. And I still need the minus sign. So our goal is to write this so that it's the delta. We're trying to figure out delta, and we know delta is 0 less than x minus c, absolute value of x minus c, less than delta. And really, we're just going to focus on the absolute value of x minus c less than delta. So if I can take this and rewrite it so that this inside is x minus c. C is what we were approaching, so we want it to say x minus 1. If I get the left side like this, whatever number I get over here is delta. So we need to do a little simplifying. 3x plus 1 minus 4, I'm going to combine the 1 minus 4. And then our goal is to have just x. And hopefully we'll get x minus 1. So to get just x, I'm going to factor out a 3. I'm going to scroll down a little bit. So if I factor out a 3, we're left with 3 times x minus 1, which is good so far. That's what we want to come out. 0.05. Nothing has happened on the right side yet. And with multiplication, you can give them each their own absolute value. Some of these steps you don't really have to write out, but I'm showing you each individual step. I'll show you where we could really skip from and to. So absolute value of 3 is positive 3. And then we don't need the parentheses inside anymore. And then we want x minus 1 alone. So we're going to divide both sides by 3. So we get x minus 1, absolute value of x minus 1, less than 0.0017. And if I remember right, it was actually, yeah, 0.0016666. I just rounded. Okay, so one more problem. So we have the limit as x approaches 4, that means 4 is our c, of x over 2 plus 1 equal to 3, so 3 is our limit. And we want to find delta such that epsilon is less than 0.01. So we still have epsilon and f of x and L. So we want to still take our formal definition for epsilon and plug in what we know. F of x is the function, x over 2 plus 1. L is 3, that was our limit, is less than epsilon. We want epsilon to be 0.01. So again, we want to simplify. We know the formal definition for delta, and I'm just going to focus on the part we really need. The absolute value of x minus c is less than delta, and we know c is 4. So we want to rewrite this. So it says x minus 4 over here so that we can figure out what delta is. So again, we combine x over 2, minus 2, 0.01. So this time, instead of factoring out, in order to make this just an x, we've got to multiply in. So we're going to multiply everything by 2, everything in here, and what you do to one side, do to the other. So we have absolute value of x minus 4 less than 0.01 times 2 is 0.02. So now, that's all we had to do on this one, because we have x minus 4 here, less than a number, so this is our delta. So hopefully that makes sense. You know, the formal definition, especially just understanding what it means, is confusing. Limits are just confusing. But hopefully these example problems show you how to solve for delta a little bit easier. So hopefully you can solve for it, even if you're still a little fuzzy on what a limit actually is. So hopefully it's helpful. Let me know if you need any more help.